Hi, my name is Kaileigh Calhoun, and I'll be a senior in the fall at Purdue University studying agricultural and natural resources engineering. This summer, I had the opportunity to participate in the Research Experience for Undergrads program through the University of Florida. I worked with Dr. Katie Miliaccio at the Tropical Research Education Center in Homestead, Florida, on my project entitled Correction of the Analysis of HFPO1 Heat Flux Sensor Data During Periods of Rainfall. My project is a contribution to the larger Snapper Creek project, a collaboration between the United States Geological Service, Miami-Dade County, Florida, South Florida Water Management District, and the University of Florida. The site is a grass well field that's located next to a canal. And the goal here is to measure the water balance at the site and all of the different components. It's important to know the water balance here so that all of the stakeholders involved can know how much water they have now and how much they'll have in the future. This is important both for planning and for distributing the water fairly. To get the water balance, we need to know evapotranspiration. And evapotranspiration can be calculated with the soil surface heat flux. Here at Snapper Creek, we have two soil heat flux sensors made by Campbell Scientific. These are buried 8 centimeters under the ground. So they measure the soil heat flux at that 8 centimeter depth. For our measurements, we need the heat flux at the surface of the soil. To find this, Campbell Scientific recommends adding a sensible storage coefficient. This coefficient is determined by the change in temperature at the 8 centimeter depth in the soil over a 15-minute interval. This method is fairly accurate when it's not raining. The values tend to peak during the day, and then at night they go down a bit. But when it rains, large negative spikes occur, and these are largely artificial. The reason for this is that when it rains, water enters the soil from above. Some of this water is retained by the soil layer, but it can also drain through to the layers below. The method suggested by Campbell Scientific assumes that the temperature of the soil is always in equilibrium. But if you put cold water on top and then let it drain down below, the temperature artificially drops to a temperature that isn't really in equilibrium. The goal of my project is to find a method for calculating soil surface heat flux that does not result in artificial spikes. To do this, we're going to try 3 different methods. The first method we're going to try is an energy balance. This assumes that radiation from the sun enters the soil, and this is equal to the heat flux due to temperature change, plus the heat flux due to phase change, plus the soil surface heat flux. And it results in this equation. The second method we're going to try is adding heat flux due to precipitation, as developed by Bogan, to the Campbell Scientific current method. So we're going to subtract off this heat flux due to precipitation, and we're going to develop it by considering the infiltration and the difference between the rain temperature and the soil temperature. And it results in this equation. The third and final method we're going to try is altering the Campbell Scientific equation with the change in volumetric water content. So this assumes that the soil surface heat flux is equal to the heat flux measured by the sensor, plus the storage in the water that's in the soil, plus the heat storage in the dry soil, and subtracting off the change in heat flux due to volumetric water content. This heat flux due to volumetric water content is important because it accounts for precipitation, drainage, and evapotranspiration. The fourth equation, developed from the change in volumetric water content, does the best job of reducing the artificially negative soil surface heat flux spikes. However, this improvement is not statistically significant, so we need to find a way to increase this reduction. In the data, the soil surface heat flux spikes and the spikes in volumetric water content don't match up exactly. So our current equation averages the time steps so that we can align these data points. However, we suggest creating a computer program that matches up the heat flux spikes and the volumetric water content spikes exactly. From there, you can create a more accurate equation that improves the reduction of the spikes. Participating in the REU this summer has been an awesome experience. I've gotten to get to know everybody in the research experience for undergrads program. We all have worked on different projects, but we talk to each other about them and get to learn about them, which is a really cool experience. I've also gotten to know everybody at Trek and learned from them and all the different things that they're learning about. I've gotten work experience and learned about all the different water issues in Florida. And a lot of these ideas are really inspiring for deciding what I want to do when I graduate.